For chapter 28, we're going to talk about reflection and refraction. The principle that dictates reflection and refraction is going to be the principle of least time. That is that a beam of light will take the least amount of time to get to one place as it possibly can go. So for a beam that is just going through air is going to travel in a straight line. However, if a beam has to be reflected off of something, if the electron configuration is a metal or something like that, where the light is reflected rather than pass through, then it is going to have to follow a different path. And what angle is it going to make when it reflects off the surface? What it turns out is that it makes an angle equal to the angle that it initially reflected or it initially came in at. That is because us, if it were to follow through, if it were to not bounce at all, it would follow through in a straight line. This means that in order to get to the point the fastest, you must follow through like you were going in a straight line, but flip it around so that it goes down. It would follow through to a straight line, flip it around, and it goes up at the same angle that it initially came through. This is action of the principle of least time. It is also something that you can just find by looking at the physical equations, but this is a good tool. As you can see in the first diagram, we have a steep angle where the angle with respect to the normal, which is the line pointing perpendicular to the surface, is small, that it will also come out at a steep angle. If you have an angle that's about 45 degrees, then it will come out at an angle of about 45 degrees. And if you have a shallow angle where the line, the angle from the surface to the incoming ray is small, but the angle from the ray to the normal or the perpendicular is large, then you're going to get another shallow reflection at that same angle. This principle of least time also comes into account when a beam of light goes from a vacuum or air, which is very close to a vacuum, to something that has a much lower speed. In order to get to a separate point as quickly as possible, or in order to get to the final point as quickly as possible, we would want our beam of light to spend most of its time where it can go as fast as possible and then only go slowly for as little amount of time as possible. That means that the angle of incidence between the normal and the ray is going to be bigger than the angle of refraction of the ray that goes into the slower object. These principles of reflection and refraction stay true throughout most cases or throughout all cases for what we're looking at. But if you have a strangely shaped mirror, then the reflection is going to be similarly strangely shaped. For example, if you have a spherical mirror or a parabolic mirror, where a parabola is the x squared shape that we were talking about when we were talking about motion through the air with kinematics, you are going to see that the normal changes direction as you go across the sphere or across the parabola. Therefore, the light that reflects off is going to lead to images that are either smaller or bigger than the image, depending on whether the mirror is smaller or bigger. So a convex mirror, which is a mirror that points outwards, is going to, in this case, give you a smaller image, while a concave mirror, which is a mirror that caves inwards, as in example B, is going to give you a larger image. You also get diffuse scattering when the reflections are just not very, when the mirror is just not very straight, and the reflections are going to be going off the normals at all these different angles. If the surface is so smooth that the distances between successive elevations on the surface are less than about 1/8 of the wavelength of the light, there's very little diffuse reflection, and the surface is said to be polished. The surface, therefore, may be polished for radiation of a long wavelength, but not polished for light of a short wavelength. The wire mesh dish shown to the right is very rough for light wavelengths, and so is hardly mirror-like, but for long wavelength radio waves, it is polished and therefore an excellent reflector. Reflection off the walls of your room is a good example of diffuse reflection. The light reflects back into the room but produces no mirror images. Unlike specular reflection, which is mirror reflection, diffuse reflection does not produce a mirror image. Refraction is further demonstrated by Snell's law, which says that if n is the index of refraction is the speed of light in vacuum over the speed of light in material, then the index of reflection in one object times sine of the angle with respect to the normal is equal to the index of refraction of the other object times sine of the angle with respect to the normal for the second object. So we can kind of see why this should be. So I personally had never seen use of the law of or the principle of least time beforehand. What I had seen was the fact that as an object or as a beam of light goes in, the distance between the peaks of the wave or the wave fronts is going to become smaller because uh, if you'll remember, speed is equal to wavelength times frequency. So as frequency has to stay the same, but speed goes down, the wavelength has to go down. Therefore, in order for the wavelengths at the interface, at the area where air meets water in this picture, in order for those uh to be at the same position on the interface, the light has to actually bend so that it is going steeper through the water than it is going through the air. So we also see refraction in Earth's atmosphere. As you might have noticed in the last lecture, at sunset, the path of light through the Earth is going to be bending. This means that there's an apparent position of the sun, even though the actual sun has already set at sunset, because the uh, air, or because the light going through the Earth's air is refracted and bent, you see a different apparent position of the sun than you see the true position. This is also accounting for mirages, where light from the sky on a hot road is bent back up towards your eyes, so it looks like the road is blue and it looks like there's water in the road, even though that's just the light from the sky being refracted through the atmosphere. I should also note that light does not go through the same material at the same speed for different wavelengths of light. This is going to mean that there is a different index of refraction, which means that there are different scattering, or which means that there are different angles that light is scattered as it goes through a material. For example, with raindrops, if you have sunlight coming into a raindrop at a certain angle, then it is generally going to come out of the spherical wave drop at scattered at different angles. So the violet light will be scattered from its initial sunlight beam at an angle of 40 degrees, and red light will be scattered from its initial sunlight beam at an angle of 42 degrees. This means that when you look at the light that's scattered from the raindrop, it is going to form a cone between 40 and 42 degrees with where you will see a bowl in the sky with all of the light scattered into different colors, which is what we call a rainbow. Another consequence of these reflection and refraction angles is total internal reflection, where if you have light that comes from a source inside of an object that has a greater index of refraction than the outside, then what will happen is that the light will bend more as it goes to the outside until eventually, as you can see on this diagram, the light will bend so that all of the light will bend inside. That is when the angle outside becomes 90 degrees, when the angle outside just starts going along the surface. That's called the critical angle for the inside. So using Snell's law, we're able to calculate this critical angle. But the main thing to note is that after you have anything steeper than this angle, then nothing can get outside, which means that all of the light is going to be reflected inside, which means that none of the light is going to be lost. This becomes interesting when we look at diamonds, which have a very high index of refraction. I think they have the highest index of refraction of any naturally occurring material or any common material, where anything greater than an angle of 24.5 degrees is going to lead to total internal reflection. So when you look at a diamond, you are only going to see these brief flashes of light that come out of the diamond because most of the light is going to be internally reflected. You also have fiber optics, which are materials with a high index of refraction where we transmit information and light and actually use this for computers, where instead of using electronic transmission, we actually transmit at close to the speed information at close to the speed of light because it is undergoing total internal reflection and not just shooting out the side. It is shooting along the fiber optic cables. One of the most obvious and most useful ideas that come from index of refraction and from the idea of refraction are lenses. So you can have a converging or a diverging lens generally, where a converging lens takes all of light that is parallel to the primary axis of the lens, as you'll see on the left-hand side, and points it through a very singular point in order to focus the light and create images. A diverging lens, on the other hand, makes it so that all of the light that comes parallel looks like it's going to be coming away from a certain point, even though that light never actually passed through that point. So a converging lens creates real images, which means that you can see them on a screen, and a diverging lens just creates images that look like they're real or that look like they came from a certain place, even though the light never actually traveled from that place. As you can see, all of the light on the left-hand side is parallel and doesn't come to a single point at any point, but when it's put through a diverging lens, it looks like it came from that point where all of the dotted lines converge on. Using this, we are able to create images of objects and bend the light so that it looks like an object is bigger or smaller than it is, or it can be flipped around, or any of these other things that are useful. So one of the things that is useful is that we have lenses in our eyes which take light, which is essentially parallel, and force them into our retinas, which is and focus them into our retinas, which is how we're able to see light, even though our eyes are a lot smaller than the world around us. There, there are, however, a couple of problems with this called aberrations, where a spherical aberration means that the light is not exactly going to go into the focus, into that one point where everything's supposed to converge for uh, different parallel rays. So something going straight through is going to go straight through to the focus, but something a little farther away is going to go to its own focus, and then something even farther away is going to go to a closer focus. And the way we get around this is that instead of doing spheres or grinding our objects into or grinding our lenses into spheres, we grind them into parabolas, which are mathematically defined to focus on a specific point. A harder problem is chromatic aberration, where different colors are going to go through the lens at different angles because, as I said, light does not have a constant speed inside of an object. It just has a different index of refraction for different colors. Therefore, as it goes through different angles, it's going to come out at different angles. And this is harder to deal with, but we can deal with it by focusing on certain types of light that we're looking at. So only using materials with laser light, which is at a certain material or a certain frequency and has different uh and has is going to only go through at certain angles that we're used to, or we can have a material that is mostly going to have as little bit of a change in the index of refraction as possible, which is going to be more practical